right? So yeah, traditionally when you're clicking the application, that you're immediately using the application, right? So what we did was we hijacked application usage and we added a little lockout test. This kind of lockout test has been used to, for safety reasons, right? So when people are doing things and ensure that you're doing the right thing, but we added a little bit of inconvenience, right? So in such a way that we can block their usage intention. So what happened was this kind of lockout test was quite useful, like slight friction, even just a sure message that really reduced the phone usage like at least 10%. But adding a little bit of effort, like adding 10 digits, significantly reduced the usage intention, right? So I talked a lot about this kind of the locking up and blocking and so on. So what is the user's perception about the lockout for the self-help? So in terms of like whether the interface itself is really coercive or the people feel stressful about this. So what is very interesting thing is that with the control, without such self-help lockout tool, with the experimental group with such a lockout tool, what happens is that people feel less in terms of the coercion and less the stress. So it's quite counterintuitive, but what happens is that with this kind of tool, what people usually say is like peace in mind, right? So I just lock up whenever I have temptations. I don't need to actually overcome that temptation. It's locked by the computers, right? So it lowers the user's burden for the self-controlling. In some way, this kind of technology is really useful for helping people. Now, I wanted to say about what is looking ahead, right? So I want to talk about two different aspects. The first one is about exploring novel data-driven intervention methodology, right? Since I talk a lot about the different types of methodology. So if you're looking at computers right now, I really talked about locking the phone, right? So that actually in the psychology they call it commitment device, right? So you're making a commitment contract by yourself and do something, right? So if you're going to the actually everyday interactions, this kind of the lockout is pretty common, right? So how many of you actually probably saw many of these ice cream fridge that blocks frequent door open. If you go to the subway, it goes one direction, not the other directions as well, right? In the car, there is an eco driving mode, so it blocks sudden acceleration. Okay, if you're using work rate like your micro brake, so you're not really continuous usage of your computers, right? So you can take a look at the traditional human-computer interaction model where the task input, core computing, and output. What happens there is you can actually add a little bit of the restraints, what is called the interaction restraints, by artificially creating some sort of the interaction gulf. So what gulf of execution and gulf of evaluation. So this kind of the gulf restraint is really compared to existing concept, it can be considered as like uncomfortable interactions or inconvenient interactions or what is called the mindful interaction. So we can systematically explore this kind of features, right? So I think that it's good to actually explore the design space of interaction restraints. And also we want to actually use intelligent and context-aware and also the proactive intervention. And of course, while we're doing so, we have to think about ethical and social responsibility in terms of design this kind of applications, right? So one of the things that we can do is that under what context we can intervene, and also when we can actually intervene. So that's opportune moments. And also we want to actually balance the user needs and target goal, and in terms of the learning the goals. And also we can do the natural language interaction with the users in terms of better doing the how to interact with the users, right? So another one is that I told you earlier about the theory-driven design based on the Bandura theory. So we need to actually leverage the theories, and also we have to actually do the experimental evaluation so that we can establish the evidence-based design principle for the digital well-being, right? The second direction is related to the broadening contextual scope of understanding the users, right? So since we have a lot of the context variable captured by the mobile technologies, people are using the phones, and what we can do is that we can systematically explore many of these problematic behaviors, which is actually underexplored by the by the people. right? So one idea that we can actually leverage from the domain of the healthcare is that we can use what is known as digital phenotyping, right? For example, here, a lot of the negative aspects of the problematic behaviors can be actually captured by all these parameters like behaviors, actual usage behaviors, and we can find some sort of mapping function like this, and so that we can have a systematic understanding about the problematic usage behaviors, right? So we can use the data itself to have more accurate and holistic understanding of the negative effect with the real data. In order for us to do that, it's imperative for us to actually secure the long-term, large-scale, and open mobile data sets for the data analysis. But at this point, such data set is really limited. One of the data set that we opened to the public was this K-Immophone data set. So, but it's small, but we need really large data sets so that we have a more systematic understanding of the problem behaviors. All right, so with that, I talk about two aspects: using the digital technologies to understand user behaviors and also help users to better self-control. And I was actually looking forward to, by using the data, we can broaden the contextual scope of the understanding users. At the same time, we can better explore the novel data-driven interventions. All right, thanks so much.
Yeah, thank you very much. Interesting topic, very relevant for this conference series in which we are also aiming to look for the meaning and the leverage of technologies for well-being and for healthcare. However, I do have a question. How do you see the metaphor between actually trying to nurture, to stimulate people to use technology in a good, sensitive, and not an addicting way? First, it's the fact that you're actually doing that by implementing and adding new interventions, for instance, steps that you have. So how do you see this balance or this metaphor?
Yeah, so I mean, so we're using technology to deal with the technology, right? So that's the approach that we're doing, right? So I think that Google and Apple, they should they introduce this kind of technology, right? So I think that it's our responsibility, right, to design technology so that people can responsibly engage with the technology. And we're not saying that this kind of tool itself is, we don't want users to be dependent on this tool either, right? So as I showed you earlier, that people do better self-control about their behavior, right? So we're actually, we can interpret this kind of tool as more like scaffolding, right? So as a scaffolding technology in such a way that they can be trained to better behave, so that they can better manage the tool, so that digital well-being as a center of the well-being, so that it can actually better influence not only the physical, mental, and social well-being. So I think that that's the right direction of this kind of using this kind of technology, right? All right. Okay.
It was really great talk. Since we use technology for helping the people, but sometimes that is abused that much. So I just wondered if you really this technology really help, but if a digital postcard, such as I used to remember my phone number, my friends. Nowadays, like I have no idea what my phone number is.
Yeah.
This technology really help them, but eventually that we so much that use it and then lose also our computers.
Yeah. Well, I totally agree. So I mean, technology, that's what Mark Wise envisioned 30 years ago. So technology become part of our body. So we're not really thinking about, without technology, we don't exist these days, right? So we don't remember, that's part of our brain. Now the thing is that how to actually responsibly using this technology so that I can flourish, right? So that's the goal. So as we design new technology, engineers should be more mindful about the negative consequences, right? Understanding, measuring. So we're saying that digital well-being by design, right? From the design phase, we should be more proactive so that we can prevent that kind of situations, negative situations.
Yeah, any other question?
Right, so let's give that to the professor.
Right. Thanks so much.
Okay, so thank you. Next professor is next invited talk we have from Professor K.C. Santosh. It is on.
Professor, you can turn on your camera so people can, yeah.
Okay. So Professor Casey is a highly accomplished AI expert, and he is the chair of Department of Computer Science, University of South Dakota. He served the National Institute of Health as a research fellow. Before that, he worked as a postdoc research scientist at the Loria Research Center, Université de Lorraine, in direct collaboration with industrial partner IHCI France. He earned his PhD in computer science, artificial intelligence from INRIA Nancy Grand Established Research Center. Professor Santosh has demonstrated expertise in AI, machine learning, pattern recognition, computer vision, and with the various application domains such as healthcare informatics, medical imaging, document imaging, and many more, and earned several high funding, more than millions, several millions, to name a few. Professor Santosh is the proud recipient of the Cutler Award for Teaching and Research Excellence, USD 2021, the President's Research Excellence Award, USD 2019, and the Ignite Award from the US Department of Health and Human Services, HHS 2014. And he served as an associate editor for many journals of repute, and is the chair of many conferences, and did so many research in the areas of healthcare, computer vision, and machine learning. So with this all, so since he has a long biography to read, and just I invite Professor Casey for his talk. Thank you.
Thank you very much for the invitation. I can't make it in person, but the conference from a distance, meaning conference, presenting online is basically another good idea, but I take. But again, thank you one more time for invitation. My name is K.C. Santosh, and I'm the chair of the Department of Computer Science at the University of South Dakota. I'm also founder and director for the Applied AI Research Lab at USD. I do a YouTube channel you probably want to follow, and I mostly do a talk educating people about AI and data science related topics. In these days, people say, how about just 2 minutes video, which is really hard for professors talk, but that's what it is. Today's talk is about human in the loop machine learning. I believe you guys learned about him or heard about him or also worked about it. And other thing that machine learning scientists always would love to take a look is how big data is big enough to begin with. Right? How big data is big enough to begin with. So that's basically for machine learning scientists. And today's talk is entirely relying on the book which is here. And this book is in press. We just have this cover page. The idea is to look at active learning. That's what we call human in the loop machine learning. And the target or objective is to minimize the possible risk of future epidemics. That's what the talk is about for today. All right. Okay, so let's move on. This is my statement, my views, opinions, and research standpoints today do not represent the university and the lab I'm associated with. These are my viewpoints, and got any concern, raise your hand or talk. We'll go from there. This is, as an administrator, if I don't say this, I feel like the talk is not complete. You see the United States of America map, and you see South Dakota. And in South Dakota, you have to see SD, logo SD, that low VSD means we are number one or the public flagship state university. What does it mean is we're 1 in 50s. Right, so anybody who would love to join USD Computer Science, please do come. I'm going to start with, I have 45 minutes. I'm going to make it a little quick. It's because it's a little late here. I came here early morning and to try and finish things right. So back in days, we don't call AI. We hardly call AI because we're scared of having this nice term. Today, AI being more fancier, more sexier, and whatever. I mean, you take them that way. We call research in computing. Regardless where you come from, either you're from energy, healthcare, agriculture, all the way up to education, everything comes today all about data-driven decision-making. And today, we call them AI-driven decision-making. What does it mean is you definitely need AI in the game. And AI has been always the deal breaker. I'm going to give you a very nice walkthrough what the AI is and why data is important. The first thing you happen to see in here is automation industry. The second one is obviously healthcare. In healthcare, what you happen to see is the high-end version of the perfect AI world. Unlike if we go back, this is just the if and else condition, right? You get to something just below me, I hit him. I keep hitting, right? That's what automation is about. Automation is not really AI, but if you happen to see healthcare, you definitely see some clinical manifestations or reason of interest. There are some reasons of interest where you happen to see some problems in there we call pathology or pulmonary abnormality findings. It's beautiful. And here, digital humanities. We're talking about graphics coming from those ancient documents. We're talking about the way they write. What does it mean is the objective is to figure out what they are, where they come from, and when it was created. Basically, we know the people, we know the culture, we know everything. Similarly, fashion industry, AI is happening everywhere. Finding a perfect couple, partner, spouse is only possible from AI, right? Did I say right? Maybe I'm talking about a little more than what I need to talk. But again, if you come all the way down to service to the needy people, that's what the AI should be happening. We see perfect world, and we see world where we still have to work on. All these problems, beautiful problems, require a big data, right? A big data, but again, nobody knows how big data is big. How many of us here looking after students? How many of us, let me rephrase this the other way around, how many of us here looking at our supervising students? How many problems you've given to them? And when you give the problem, the students or research scientists came up with the results saying that, Professor, I can make better results if you give me some time to collect more data. How about that? This is conventional ask, request, or statement arguments from everybody across the globe. Yes, we need big data. We need a beautiful supercomputing machine, right? Very high-end infrastructure so I can crunch any sort of data, small, big, whatever, or complicated data, and I make a decision-making without bias. That's what the need is, and question is, everybody requires big data. Let's move down to medical imaging informatics. I've got 3 data sites. I wouldn't have to pronounce in here, but one is Montgomery County data site, second one is Shenzhen Hospital, and third one is India. Meaning 3 different continents, okay? I intentionally collect 3 different data sites coming from 3 different regions. A reason behind this is to take a look if we can make cross-population train and test model. That's the beautiful idea. Wish we could have made this and saved thousands of people during the COVID-19 pandemic in the year 2020 and 2021. This is the data coming from tuberculosis. I say TB, okay, T Tom, B black. And then I do experiments right away using machine learning model. We're not looking at a conventional machine learning model. We're trying to learn, okay, according to title, we're trying to learn how big data is big enough for me to start with. Can I get 100% area under the curve if I increase the data? That was the idea, right? So what happened is we're trying to see cross-population train test model using handcrafted features that everybody can do, right? Why not? You come up with the idea of deep learning model. That's a bit better idea, but question is not that. What are handcrafted features? We got 96% area under the curve in here. Handcrafted features, for instance, understanding the ribs even after an attack from pneumonia or tuberculosis, clinical manifestations, all problems. Those ribs are not visible. Understanding the ribs orientation exactly the way radiologists do is one way to follow clinical procedure in computer vision. That's why applying pyramid of histogram of gradient is the best idea to take a look how ribs been oriented, right? You don't see ribs. It's basically a snowstorm with no leaves in the tree branches falling down or so, right? Which is one way. Second way, the other way, there are plenty of ways that we've been doing those long section analysis. So the other way is using SIP context. In computer vision, this is the beautiful SIP descriptor that everybody's been using, right? Probably around 2001. Source Balanzi implemented SIP context, SIP descriptor, and today it's been popular everywhere for every problem. Understanding the SIP as precise as it can be. I can go for the SIP matching for both lung section. If one of the lung sections having a problem, then I can really go for the deal. Yes, this guy has a problem, so there is no symmetry. Here we're looking at symmetry exactly the way doctors do, right? So what happens next is you definitely come up with area under the curve. I'm trying to tell you, I'm using all possible data collected so far for years, and I get this result. And the area under the curve in here almost close to 96-97%, which is we call a good thing, right? And I did not do no deep learning in here. Deep learning is completely different in terms of understanding sensitive features or clinical manifestations. What if I have foreign elements like rings, nipples, and jewelries and everything? Do you think deep learning alone can figure out? Which is almost impossible to do it. Now I give you a clear walkthrough that we need data. Based on the data, we train the model and we test him, and the test comes up with the good results. Now let's have a problem. Problem is future epidemics. COVID-19 is one of the examples that we have just faced, and future epidemics is inevitable and it's possible. What if I don't have data? What if I should start a machine learning model from the first day? Do you think you're going to wait for the data for several months, years, and you collect data, you train the model, and by the time no people survive, you're not going to test your model in the cemetery? Can you do this? Is it possible? Then it is a time for us to think, what is a complete data? If the data is not complete, what do you understand about prediction? And in back in days, sometime in 2020, I happened to see hundreds of thousands of papers on prediction or predictive modeling for COVID-19, basically predicting how many people will be infected and how many people will be died. With less amount of data, did we not just realize that we need enough data to understand everything at one end to the other end? Or we need enough data or complete data to understand the whole story about what's happening. If I don't know that much, do you think I predict right? Then we come up with this. This paper, I published COVID-19 prediction models and unexploited data, basically telling you an idea of so many unprecedented events which cannot be parameterized in mathematical modeling. How do you parameterize test capacity rate of the hospital? How can you parameterize immunocompromised people? How do you see the salary going down, basically reduction in salary because you work from home, and the food habit after you don't have money to buy food? Those things, since cannot be parameterized, it's almost impossible to predict what is next. So we can only predict the range. The second thing, according to the picture in here, the blue line, a camel hump or our Gaussian data distribution will tell you the fact that everybody is consistently telling the exact same event, while the gray one, the flat one, right? The flat one are basically giving us a sparse data distribution. And back in days, we call flatten the curve because they don't talk about exact same event. They only go far from each other. Flatten the curve meaning we don't talk to each other. We have to be away from each other. That's why the data does not consistently tell the same story, and it's impossible to predict. The beautiful prediction that we can do is fitting the curve. And we got 70-something data, and it's in the book that I said it's just garbage in, garbage out. Fitting the curve is not prediction. At the same time, data visualization is not prediction, which you happen to see in all social network, LinkedIn, Facebook, Twitter, and everything. Something is wrong. So what I'm trying to tell is data visualization is not prediction, and then people published paper like hell. That many we don't know. Basically, it's another propaganda. Remember, we keep talking about data. We need better data. We need better data. We need big data so we can predict. That's what the idea is. Now, let's take a look. Some of the papers back in 2020 and 2021 published based on deep learning models. Understanding the data sentiments is very important. It is not just the data, by the way. Okay, so deep learning for prediction with hundreds of data, just hundreds of data, 100 days, 100 data, and having thousands of parameters in deep learning model and predicting 100 data for the next 10 days is almost impossible. In this case, we are predicting deep learning parameters, not the prediction of how many people will die or estimated infection. That's a horrible story because people just don't understand what they predict. They predict parameters because kind of wrong. That's why machine learning scientists should be looking at the right tool. We call finding the right tool. You got two projects here. One, you drink coffee with your girlfriend. Second, you have to clean your driveway before you head to the office. And you have two tools available. One is shovel, and other one is spoon. If you come up with the shovel and drink your coffee with your girlfriend, I don't think the girlfriend is going to stay more than 2 minutes, 2 seconds. You're crazy. He's gone. He's sick. So girlfriend is going to leave right away. But at the same time, if you take the spoon to clean your driveway, You will take months to complete your driveway. You never take the car from the garage. Your wife or your spouse or your kids will look at you through the window. What happened to the dad today? Something is weird. Finding the right tool is important. That's what I'm talking about. Having a deep learning model is fancy and sexy enough to be employed. But the question is, do you want to use a shovel for a coffee and a spoon for a cleaning driveway? It's up to you. By the way, you don't want to be looking crazy. So here, typical machine learning model, get big data. Basically, I'm trying to help you understand this is one-way test. You get the data, you train the model, and you make the decision. You get the unknown test sample, you get the decision. Do you learn something? You basically did not learn. You learned 2 days ago. You keep testing today. Why not, when you get misclassified samples, and you know this is your 92% accuracy, why not use that misclassified samples, get back to the training and learn every day? We don't typically do. That means this is one-way test. Is this just automation? Yes. People call it artificial intelligence. Artificial intelligence, in other words, is about augmenting human intelligence. Humans, when they make mistakes, they learn by itself. Did you see we learn when we make mistakes in this example, in this picture? No, it's just the one-way test. We test how much I have learned last month, meaning just based on the training samples. I keep changing training, but I did not learn incrementally. Question is, now back to the same story. In medical and imaging informatics, the question is how big data is big enough to start. And here is a sarcasm paper. The paper says COVID-19 imaging tools, how big data is big. I'm so sick and tired by looking at those papers, and I'm just done with them. That's the reason that I published this paper. Let's go back and take a look. What people did, people started with 25 images in immediately after COVID-19. We get to see COVID-19 from 71 images all the way up to 18,000 or something images. Did you see any increment, or sometime you get 100% area under the curve as well? The idea of the purpose of this study should not be always about the big data. It is about whether I miss all possible clinical manifestations in the data or sample. Right? We did not really see. We will never go above 100%. If we go, that should be a complete linear data. In a real world, a complicated world, it's not going to happen. Same thing happened for CT scans. We're talking about chest X-ray, and we're talking about CT scan. Starting from 102 images all the way to 30,000, I don't see that much change in terms of accuracy. But if you look at robustness, probably yes. More data, you get more data, more complications. We didn't say the following things. None of the papers in here, all here and here, did talk about model fitting. They only talk about, I get 99, how about yours? I get 92, how about yours? Oh, I beat you by 2%. This is the significant change. Come on. If this is the way, there is one book coming up from my desk, which is Building Machine Learning Models is Not Innovation. We did not talk about architecture. Nobody talks about model fitting issues. Everything happens because I get 99%. That means it's garbage in, garbage out. Data augmentation is a beautiful term in computer vision, while in sensitive healthcare, medical imaging informatics case, do you think it's going to work exactly the way in typical computer vision problems? Maybe not. I'm going to show you one example. How about transfer learning in COVID-19? The transfer learning in computer vision and machine learning lingo, it's beautiful. but can I get something learned about pneumonia and go test COVID-19? It is possible. It's because the architecture remains the same. It is possible. Let's make it analogy with the doctor. It is possible because the doctor is an infectious disease specialist, and he can test COVID-19. But do you believe that he's going to know everything about it? That's why they took 6 months to understand from November, December 2019, all the way up to spring, which is March. It is possible that we can use radiologists who are good at analyzing chest X-rays, but typically pneumonia, but it is almost not possible, or basically it's kind of yes or no. We may not use the same doctor for a clinical manifestation due to COVID-19. Data augmentation in healthcare is very, very sensitive, which I did just talk about before. You have the right image. This is your image, the first image. And then when we do augmentation, we just flip, we change the orientation, we move some parts of the pixels from here to the other side. We keep doing what we can do. It's basically flipping this, that, rotation, changing the location of the pixels. Now it's a time for us to think. The data augmentation, do you think it brings us a clinical manifestation due to COVID-19? Yes, we got more data type, but we samples. We change it, we flip it, we make it go this way, that way. We hang him there. But do you think changing the location of the pixels would bring you the exact clinical manifestations or pathologies due to disease X, which is impossible? Data augmentation don't give us clinical manifestations or significance. There is no point to say that I can detect COVID-19 due to data augmentation. But what is important for a computer vision scientist or machine learning scientist should say, and what's important is, yes, my system is robust, not more than that. That's why in healthcare machine learning, we still have to do so many things. I repeat, data augmentation, increasing samples just by flipping, changing location of the pixels don't give us any real clinical manifestations due to any disease or disease X that could be COVID-19. Right? So what is required then? The required is a need of active learning, the need for cross-population trained test models, the need for multimodal learning and representation. That was the paper immediately after COVID-19 announced, I published in 2020. The reason behind this is you may have multiple different modalities, meaning too many different types of data for a same guy, same person. Data 1, data 2, data 3, and this is a time series data. We keep testing everybody because something happens not nice and unusual. Do you think I'm going to create COVID-19 expert? No. Do you think we have we have doctors with pneumonia or tuberculosis expert? Yes. Do you think you have a infectious disease specialist? Yes. That's we get trained. But the question is, we don't really have COVID-19 expert. That means the pre-trained doctors, I'm talking about those doctors now, pre-trained. These pre-trained deep learning models can be used to understand unusual behavior happening due to pneumonia, due to COVID-19, very close to pneumonia. And we learn every day from the first sample all the way up to thousands of samples, like the way doctors learn from the first day. And when I ensemble all these decisions coming from different outputs, basically they talk about the same events and beautiful thing. This was the first conceptual paper I published in 2020. Based on that, we come up with the idea of mentoring. What is active learning? Active learning, in other words, we call human-in-the-loop machine learning. So question is, how much data I need to start? That was the talk, right? That's the talk today. If I'm looking at hundreds of samples and after that I let the system fly by itself, then how about mentoring? Who is going to mentor? Do you think I can have the machine learning model ready in parallel with the doctors from the first day when COVID-19 come in? Think about it. The question is, when do you think your kid is now ready to live their life independently? Think about this. There is an analogy, and it's in the book as well. We published an idea of agreeing to disagree. Back in way far in 2016, the publication did take a little time. It's because somebody or reviewers did have a hard time to understand the idea. Took time, but the idea was implemented sometime in 2011 or 12. And it took us a little time because when reviewers don't know nothing, it happens. So you have a kid, like the kid learns every day from their parents and the teacher. We can mentor them with little data, little amount of data every day is enough. Going from alphabet A to G and 0 to 1 numbers, he will learn and she will learn. But by 18 years, we stop mentoring. You're good to go. 18 years is a magic number that we happen to have in our human life. It does not mean that after 18 years, he don't make mistakes. That's what we're looking at. After 18 years, if a person is about to make a mistake or makes a mistake, he knows how to correct him. Remember, in machine learning, we have reinforcement learning, beautiful mechanism, which is the reward-based learning. In reward-based learning, what you learn before 18 is enough to help yourself to go for correcting mistakes from one end to the other end. And that's what the idea is. So here is how it works. You have time series data of any data type M. It can be COVID-19, chest X-ray. It can be CT scan. It can be cough sound. It can be any type. And we have deep features based on pre-trained models, like I said, those radiologists, and you do classify based on what you see. Here is an example. The first day I got one chest X-ray. My machine is ready to learn. The chest X-ray is going to give it, the pre-trained model is going to give me deep features. I didn't see nobody. The first sample, there is nothing I can do. I just keep in one pocket, which is class number 1. Second day, I got the next one. You know what I'm saying, going to do? Did I see that before? If not, this is going to be the next pocket. I'm trying to help you understand healthy and unhealthy cases, just 2 cases. I can make it multi-class problem later, okay? The third day, I got a third sample. I'm going to take which one is closer. Do I have to learn the COVID-19 is going to look like that? No. I take, that's basically pocket number 1. I keep making clusters completely unsupervised. But if I make a mistake, we have humans in the loop. That's what we call closed loop control system. Remember, I did say, in conventional machine learning model, we get the data, we train the model, we test it. Do you see any time you make mistakes in coming back? Never. Now here, we make mistakes, we're coming back. We call doctors help in every possible moment when a machine commits a mistake. Question is mentoring, right? I said mentoring. Mentoring happens only when a machine makes mistakes. Otherwise, we don't need to have mentoring, right? What I'm saying one more time is doctors take a look where the machines go exactly the way they go in terms of making decisions or decision making. Remember, question is, how am I going to do this? When to stop mentoring, right? That's the question. So 2 different data sites. I'm not going to take a lot of time in here. The story about this slide is, if you get to see multimodal learning and representation, too many different types of data for the same event E, which is COVID-19, have the AI model ready, you definitely have a consistency or high-level confidence in decision-making. I can spend time here for many minutes, but let's not spend it. Idea is to take a look, cross-population trend test model. I train the model in Chinese data site, and I do test the model in Montgomery County. Remember, if we had cross-population trend test model back in 2020 and 2021, we could have been able to save thousands of lives. We didn't have that. Our unsupervised clustering, remember, unsupervised clustering always depend on these two criteria. The criteria number one is inter-cluster distance, and the second one is intra-cluster distance. We have some different indices, Johnson index, Davis-Boolean silhouettes, and so on. We're not talking about these. Here is the experiment with active learning. We do try all possible, meaning three different modalities. One is cough sound. Idea is my cough sound COVID-19? That was the proposal. CT scan, is that CT scan COVID-19? Right, infected. Chest X-ray, exactly the same. We take that many data, and here is the result. Results in terms of COVID cough sound don't look that much fancy, but if you look at comparison, we're doing better. Here, if you look at M1, too many numbers, don't worry too much. M1, this is coming from the book. M1 is we do mentoring only first 200. M2, 600. We keep increasing the mentoring numbers is because we try to see if we miss to mentor the machine, right? That's why we come up with different results when we keep mentoring all the way up to 1210. But if we keep increasing the number of samples in a mentoring list, it doesn't make any difference. But here, the good thing that we got from cough sound is 98% specificity, which is silver lining. We didn't run over anybody, but it is a silver lining. Reason behind this is a crowd-sourced data. The data is not from hospital settings. It's a difficult data. But if you come up with CT scans, our results in CT scans give us 94% area under the curve, 87% accuracy, 90% specificity, and 85%, which is very close and comparable with those many state-of-the-art results where they have hundreds of thousands of images got trained, but we have not trained nothing. Okay? I repeat, active learning does not require training samples. They go from the first day, get trained by itself. Look now, if the results are really comparable with those machines got trained by thousands of images, this is beautiful. Same for chest X-rays, and chest X-rays are active learning is giving us 99% area under the curve, 99% specificity and sensitivity, and accuracy is 96. We definitely beat in the following, based on the following reason. Number one, we did not train our model on thousands of images. We start learning by itself, completely unsupervised, based on reward-based learning, even after mentoring, right? That's what. Message number two, the first message is a shovel and a spoon. Message number two that you are going to get today, you are not required to wait for months and years to collect data. Otherwise, we have nobody to test, meaning people already have died. We don't go to a cemetery for the test, right? So active learning is possible. Remember, when you talk with your students, you basically want to talk in a way that we look for the world, and our research should go for the research community and save the people. Again, I do YouTube channel for topic-based lecture. If you want to follow, thank you very much. And once again, I feel like we have Q&A time, and I do mostly multimodal learning and representation. Active learning is my passion. And green computing, by the way, with supercomputing infrastructure, you always have to produce carbon footprint. Then it's not a good way to look at the problem. That's why green computing is one of my beautiful topics working on for years. And generalized AI, which is very close to human AI, and graph neural network. These are beautiful things that keep working. And I would say thank you very much for Q&A.
Thank you very much, Dr. Santosh. Do you have any question about this?
Professor, can I ask?
Yes, please.
Yeah, first of all, I would like to thank you. It's for wonderful talk giving for the input for the researchers and AI community, and also complete human related thing you have dealt with the medical thing. My question is that, so you have discussed the medical aspect AI context. If you take the COVID issue kind of thing, our model, as you said, the models will not really give the outcome kind of thing. So if that is the case, so as you are expert in the generated AI context, what kind of intuitions that will help us to building a correct models or correct system to deal with the healthcare aspects of the AI concept? Because people are saying that AI is going to destruct the system kind of thing, but we believe that AI will never destruct the things. It is the human intervention only destruct. So can you light on this argument?
Thank you very much for liking the talk. Regarding AI, I kept telling or giving my arguments to people that there was a time we call research in computing. That's where I started, and today everybody wants to do AI, and everybody is AI. The things are rough, and people don't know what's in there. AI is not just a ChatGPT, and ChatGPT is just the chatbot. This is an example for educators. Remember, AI is only valuable when we know the data sentiments. That's why I came up with the idea and showing some of the data augmentation problems in healthcare. This is very sensitive. We don't really commercialize software or AI model in healthcare without understanding what's happening. That's why people come up with the black box. Honestly, for computer scientists, the black box should not be the term. It's because the neural network we develop always give us the same results. Then why it is black box, right? But for the layman, it is a black box because we did really follow clinical procedure. For instance, if I look at the problem and just make a decision, I'm assuming I'm a doctor. I know what am I doing. I know those clinical procedure 1, 2, 3, 4, but I don't see those things in neural network. And so that's why they come black box, not because it doesn't produce or reproduce the same results. Understanding is not right. Everybody wants to be AI. It's the AI world, but one day I'm 100% sure that it's a muddy water. It will take a little time to segregate where the rock's gonna go, where the sand is gonna go. We'll wait. Don't worry. Thank you very much one more time.
Thank you, sir. So with the argument, we can say from our conference and other thing, so AI can enhance the human ability and also employment and the opportunities, not the destructing the human things. I think this, with your talk, we can send this good message to the world. Thank you.
Correct. Thank you.
Thank you, Professor Santosh. I really liked your ideas and the whole presentation, and it coincides with my view also. But we are facing a problem that, if you see the development of big data and machine learning things, now it has also arisen because of the failure of the human being. That we have to see. So, curve fitting is a very old thing in the computer vision. And human did fail. Human also did fail. The problem is that we have to utilize the big chunking machine learning things also in our own way.
Correct.
So there I am trying to see that if you have done some experiments on incremental learning, because what is the problem is that human works separately and the machine works separately, and at some time they fail. The question is that how they will contribute to each other. So if machine has learned something, can we learn? The human being can learn, and vice versa. If the human being has learned something, can it tell to the machine, you start from here, not from the beginning.
So, thank you.
I come to this.
Yeah, thank you. But again, if you look at a problem of here, I'm going to show you a beautiful thing again. Start with this one. We keep learning, but at the age of 18, we say you're free, my boy. Have girlfriends as many as you want and have a good life. Do you think that day my son, who is 18, don't make mistakes? He's going to make mistakes. But the question is, what he learns from us, from me, and from his friends and teachers. The reward-based learning, don't forget, reinforcement learning, that's how we teach. Reward-based learning will help him correct. I'm a runner. I do run every day, and I'm going to tell you here, if I get to see a guy run good, I just need to kick him at some point. After 5 minutes, I kick him, dude, let's go. So he can do the task. He keeps learning, but I just have to kick him. That's what we call only when machines make mistake. We need a closed loop feedback control system. Doctors just say, oh, dude, this is not what you should do. So that's a different cluster. So I can update cluster incrementally with the help of humans. That's why we need to have humans in the loop. Remember, the machines keep learning. Humans keep learning. Question is, we're not basically transferring, we're helping each other. Why not we kept this one in place at the time we had COVID-19 happening in China and helped Italy? Why are we so much worried about, I need data? Dude, by the time all people die, and you go to cemetery for the test. That was the message. That's the book that I was basically, this book is coming out from my frustrations looking at machine learning scientists. By the way, it took me 3 hours to implement, and my code is in GitHub. Everybody can use that one. My code is in GitHub. It's a frustration. We have to learn. We will learn. Otherwise, we cannot just go, okay, after 2 years, my model is ready. Let's go find the cemetery. We cannot go to cemetery that way. Think about it. Most of these research papers, somewhere, I gave a sarcasm talk in here. Look, I beat you, you beat me. This is not the way academic institutions should stand today. This is what it is. I beat you. Oh, yeah, you beat me too. Come on, I'll beat you tomorrow. Then I come up with some other numbers to beat you. This is not how we do. At the same time, can we make our model explainable enough for those doctors so they can use it? I'm not saying that neural network is not explainable. Neural network is beautiful. You get drunk, you click, compile, get the same result. You have a beautiful day with your girlfriend, have a coffee or wine, whatever you prefer, and you click the compile button. You get the same result. That means it's already been reproducible. Now the question is, can I do all kind of crazy stuff? Do you think the CT scan is going to go this way, that way, and then you do this one? You cannot just to take one to come around to here. That's something not right to healthcare or medical imaging informatics, because we don't really see the sentimental value of the data. We didn't do any value-added product. We do always, yes, I build the model, right? What I'm trying to tell is building machine learning models is not innovation. That's my upcoming book, which is going to come by December. So this is another sarcasm work. And again, thank you very much.